Okay. Okay. Hi, I'm Alex. Today I'm going to talk about tunable automation. This is how Verisk manages proof context, and we also will get in a little bit of slicing to somewhat quantify automation. So short introduction to Verisk. Verisk is an auto-active program verifier for Rust programs. Lots of system and security projects use Verisk now. You can see them from this on this link. It's used by Amazon to verify some production code. I think this is the one I can mention. And it has relatively faster verification time compared to tools like Dafny. Because one, it leverages the Rust type system. For heap reasoning, we don't do implicit dynamic frames. It also has a more conservative SMT encoding, which I'll get into later. So just to get you familiar with the various syntax, we have spec functions and proof functions, which are ghost functions, what would be arrays and compile time. Spec functions are just like total math functions. It's like Dafny functions. For proof functions, it's like Dafny lemmas, so you can write pre and post conditions and prove things about your spec functions. And we also have executable functions, which are not arrays at compile time, and you can write pre and post conditions that will be checked by the SMT solver, and this will get compiled to an executable. So quantification. It is the primary source of automation for these auto-active theorem provers. It's also the primary source of incompleteness when the solver says unknown. In auto-active theorem provers, we often use user-level triggers. Dafny hides it pretty well, but to guide quantifier instantiation. And here's a short example on how the triggers works. So here I have a spec function is even, saying that umod2 will be 0. I have a lemma saying that my sequence is greater than 5, and every element in the sequence is an even number. And here, however, if I said I want to say the fourth element in the sequence, mods2 equals 0, this fails. This is because I put the trigger here, and the trigger is on the expression, the compound expression of the function composition of is even with a field access. However, I don't have a field. I don't have the call to is even here. So this kind of expression will only be instantiated for ground terms like is even and with a call to the field access. So one way to fix this is to manually put the ground term in. So you can assert that the fourth element is even, and this automatically instantiates this for all with the desired ground term. So another way is to have a freer trigger. We can push the trigger in and put it on the field access so that any field access will instantiate this for all, just like this. So another kind of context for y'all is there, like the Ada core talk, there's an implicit context for these in these auto-active theorem provers. So here's an example that I have two sequences, one that has length greater than 10, one has length greater than 20. If you append them together, I want to say their length is greater than 30. This implicitly uses this axiom that reasons between appending sequences and how their lengths, mostly because these are undeterminate functions. And I'll get into this broadcast thing later. So Verisk has this conservative design for verification performance, which normally leads to more manual proofs. There's no preconditions for spec functions because you want to encode them as total math functions. This is a choice also done in Boogie. There's a limited prelude. In Dafny, there are actually more axioms than you needed. There are some axioms that you can just prove directly with a smaller set of axioms. So in Verisk, there's a smaller set of axioms, and we prove a bunch of the axioms and lemmas. The axioms in Dafny. There's no nonlinear reasoning by default, and there's a more restrictive automatic trigger selection, which I'll also get into later. So kind of the spectrum of this project is to see how we can increase automation in Verisk by pushing it closer to Dafny, and we explore two axes. One is more implicit context, or have freer triggers. So to manage proof context on user level, we introduced this mechanism called broadcast. And these broadcasted lemmas can be imported at any level right after the Verisk macro in modules and proof functions and local proof blocks guided by an insert by and in the calculational proofs. So here's an example. I have a sequence of integers A. I push an element 3 to it, and I want to say that the sequence B contains this element that I just pushed in. This fails to verify automatically because Varus is unable to infer this lemma, saying that if I push and then I ask to contain, whether that element is the same one I just pushed or the sequence contains that element originally. But you can write a manual proof like by some sort of induction. And what you can do is you can mark this proof as a broadcast proof. And this will be semantically equivalent to pushing all of the input parameters to be for all guided, like an axiom. And this is all done manually in Dafny', verifiers, and Y3. They're either called auto-lemmas or lemma functions. And this is also the reason. So since all of the input parameters will be universally quantified, you also need to provide a trigger annotation for it. So once marked at broadcast, then you can import this broadcasted proof into your function by this broadcast use thing. And now the thing automatically verifies because of the increased context, and you know which axiom or which lemma to instantiate. And this is exactly how we restructure the Varus standard library on these collection types. So in the past, we have all of these extra Dafny axioms now proven in Varus, and we throw them into a large group, universally quantified all of them, and throw them into this huge lemma. And with this broadcast proofs, we can also group them together in chunks, and we can import at bulk for all of these lemmas. And this is exactly how we organize our code base. And so you may not want to find this lemma C contains lemma. What you can also do is just import this huge bulk. But then you might be concerned because now you're increasing the proof context by a lot. So if you're worried about verification performance, we also read the unstacked core from the SMT solver, and this will tell you that for this thing to verify, you're using this group, and in particular, you're using this lemma. So what you can do is, OK, now let's just shrink the context guided by this unstacked core. And with this mechanism, we also have a nice way to modularize proof libraries, especially on user-defined abstractions. So in one of the projects, we have a trait of keys. And for this trait of keys, for any instance of this trait that needs to prove the obligations, most likely like your key works like you have a partial order on the keys. And then you can mark some of the properties on this key, like the partial orderness, as a broadcast proof, and you can group them together so that you can have a user-level axiom set about user-defined abstractions. And this is also done, we rewrite one of the projects to use this abstraction, which works out pretty nicely. So now with this background, we can talk about how we explore the automation trade-off. So I just talked about there are a bunch of Dafny axioms that we manually proven in Varus. These are grouped as like these group seek properties and these collection data type stuff. So one way we can just broadcast all of them in some existing projects and see how impactful it is. So, and there are two questions, right? One, how much does it improve automation, and what do I mean by this? And the second one is if this blows up your verification project by like a long verification time or even proof fails. So we studied 4 projects, all written in Varus. I'm not going to go into them. You just need to know they exist. And to quantify automation, we need to introduce some sort of metric. And here we just looked at the number of asserts. However, most of these projects doesn't start with the minimum number of asserts because you might want to guess what the proof state is. Some might be useful for documentation purposes. So what we do is we have a syntactic tool to minimize the number of asserts in a project. This is, of course, not the real minimum. We are not doing a combinatorial thing. We're just doing a linear scan, looked at assert, remove it, see if the project still verifies. If it still verifies, then keep it removed. And another limitation is we're only targeting assertion. So we're not targeting lemma calls for complicacies. So as I said, we're trying to broadcast a bunch of stuff. So what we can do is we can minimize the projects in one run, and we can broadcast all of these stuff, and then minimize them again and compare their difference to see how impactful these group properties are. So here you can see, actually one interesting observation is that more than half of the asserts in these projects are not useful for the SMT solver to find the proof, which is interesting. And for the broadcast, around 2 to 8% of manual assertions can be removed. And for the verification time, you can see there's a large vertical line here, meaning that most of the functions verifies about the same time as before. Only like 1.8% of functions verify them more than 2 times of their original verification time. And this is kind of exactly what we want with this user-level control of automation, so that for these problematic functions, you don't need to broadcast all of these extra facts to speed up verification time. And next, I want to talk a little bit about triggers. So in Varus, the automatic trigger selection only selects one trigger in multiple possible triggering candidates. So for this universally quantified expression, you have F, G, and H, which are all like Boolean predicates. And there are lots of valid trigger candidates. For valid trigger candidates, it only needs to cover all of the X and Y so that you know how to instantiate them. However, some are useless candidates because, for example, this one will always be triggered by just having the trigger on H. So normally you take the minimum cover, which is this all trigger expression. So what we can do is see if we can move from the default or the user-provided manual triggers to this all trigger thing and see how impactful this is. So one thing we can look at is, well, we have this group seek properties, whether we can free the triggers in these more like Dafny axioms. And the answer is no. Like no, OK. You cannot free these triggers without causing an explosion in the trigger instantiation. So this S1 and S2 are just like the the X and Y's in the previous example. So the other valid trigger groups will be put a trigger on these 2 expressions. However, these will match on any 2 calls to length of a sequence, causing explosion. So another place to have freer triggers is on user-introduced universal quantification in those lemmas. And this is what we did in one of the smaller projects, IronKV. We replaced all of the trigger annotations, if possible, to all triggers. There's one proof that broke, and we omitted it because of context manipulation. And we run the same minimization thing on it. And you can see that this actually is more impactful than like increasing the ambient facts. We're broadcasting a bunch of stuff. And for the verification time, there's a slight decrease, but it also works out somewhat fine. But it's less clear to us. So it has a non-trivial impact, but it's less clear to us how do you manipulate these stuff automatically. And one future direction might be to annotate multiple trigger groups. If you want a more automatic version, you can try to be freer with triggers. And that's all. Thank you for listening. And there's a preprint available online on arXiv.
Any questions?
So about the use of these broadcast lemmas, or like use or not use. I mean, as a user who is not aware that I should use these lemmas, or like how do I approach a program when I want to prove some things about sequences? And in particular, for example, Varus errors. Sometimes like I think there's been some improvement, but it's not so clear. Like maybe it should be like for the user guidance. Okay, you can find this lemma and try to use this lemma. Like, and also in terms of minimization. Maybe like, do I really need to actually import the lemma when you said that you can actually automatically perform this, like import the whole block, then reduce to the actually useful lemma?
So I think one of the things is like we want to see how many conservative choices in Varus are valid. The reason, and like by importing these lemmas by default, yes, you can kind of import all of these properties lemmas by default and try to see how it goes. It's just not done in default because initially we want faster verification time. And for the other question, So there's currently a PR called Sledgehammer. The name is probably going to be changed. It does some sort of semantic search on what kind of stuff you can be broadcasted. I think you can kind of go pretty wild in this direction. Like technically every lemma that you wrote can be a broadcasted lemma. And you can do some sort of semantic search and see if it automatically verifies, but this is all in the future. And yeah.
And actually, also for the triggers, because it's just like somehow the same problem. Like because I was using like some, just not using really, but like playing with Dafny with some, and then using Verus, and then suddenly like maybe in Dafny there are also trigger issues, but like in Verus suddenly like these trigger issues appear, and usually like there is like this default like some warning.